pre-calculus slash calculus. We're chapter 3 in calculus, 3.1 derivative of a function. So this is going to lean heavily on what we did in the previous video on 2.4. If you remember, in video 2.4 we were calculating tangent slopes using our f of x plus h minus f of x over h definition as the limit approached 0, right? So that was our that was pretty much our infinitesimal rise over run, right? Our run being a known distance h, and then the infinitesimal shift of the x value. Again, I'm using x instead of a. Your book uses f of a plus h minus f of a. F of x plus h is a little more common notation. It's what I'm more used to, and it's probably what you're used to as far as the advanced math book goes. And also, the reason why I use f of x plus h is because of this right here. These eventually all lead into what are called derivatives, and the tangent slope is more or less the idea of what a derivative is. A derivative is a tangent slope, or another way to think of it, a derivative is the f prime or the inverse function. Well, it's not so much the inverse, but it's called the f prime function of a given function, which would make it the tangent slope of that function, right? The good thing about derivatives is they help us find instantaneous rates of change, right? So whereas before our secant slopes and our rates of change were over intervals of time, since the nature of derivatives is to do the limit as the interval of time approaches 0, i.e. finding the slope using 1 point instead of 2, it's an instantaneous rate of change. So we know the rate or the speed at that exact instant or moment, which is incredibly valuable. It's the basis of what makes calculus so valuable and what caused such a boom in math and science in the 1700s, 17th century, 1600s, 17th century, right? Into the 1800s, into the 1700s and the 18th century. Anyways, let's talk about what a derivative is, okay? So more or less what a derivative is whenever a tangent slope has a limit that exists as this infinitesimal shift approaches 0, that's what a derivative is. So that's why I say derivatives are tangent slopes. So if there's a tangent slope that can't exist, then it is a derivative. Let's see here. What else can we say? Oh, okay. So if the domain of f prime, or the set of points in the domain of f for which the limit exists, may be smaller than the domain of f, more or less what they're saying is that if f prime, or if the derivative exists, that if f prime exists, then we have a derivative that is differentiable at x. And differentiable just means that it's a function that can be differentiable at every single point in its domain. All right. What does all of that mean? More or less it means that these are consistent and they work back and forth for every single possible point on the function. So in layman's terms, it doesn't matter what value of x I plug into the function, it will work. So that's what a derivative has to be. It's kind of like looking at the relationship of a function. You know, you can't have an x input with no y output, right? There has to be an output. And it's kind of using that same logic to understand what a differentiable function is, i.e. a function that can have a derivative. So let's talk about applying the definition. So the definition is more or less what happens when we solve this function, or it's not solve, sorry, it's when we simplify and rewrite this function. So this is a lot of that algebra that we got very used to in the advanced math book. So for example, they want us to find the derivative of f of x cubed. So let's just do some quick examples on how this works. So I have to find the derivative of f of x equals x cubed. So if we remember, the way that this definition works is I have to do the limit as h approaches 0 of f of x plus h minus f of x all over h. So if I'm doing x cubed, oh no, that's annoying. I have to do x plus h cubed minus f of x cubed. Great. So if I were to simplify this and rewrite it, I don't know why I wrote it so big. Let's go to the smaller marker. Let's find out, well, f of x cubed, that's easy. Got that one, right? Let's find out what f of x plus h cubed is. So if I was going to do x plus h cubed, I could just use was Pascal's triangle, right? That's what I'm going to do. I'm going to use Pascal's triangle, right? So if I go down to the third level of Pascal's triangle, I have 1, 3, 3, 1. So my coefficients will be 1, 3, 3, 3, 1. And then if I count my exponents, I'm going to have x cubed, 3x squared h plus 3xh squared, and then plus h cubed. Cool. That is x plus h cubed. All right, and then also I'm going to have minus x cubed on the end there, right, because of that minus f of x. This will all be over the letter h. So once I simplify this, so good use of Pascal's triangle and some polynomial function foiling. So that made that very nice and quick. So let's see here. These cancel. And then it looks like I've got 3 terms with h, so I can factor h out. So this will get rewritten as h over h parentheses will be 3x squared plus 3x plus h squared, right? That cancels, right? And then if I do the limit of 3x squared plus 3x, was it 3xh, whoops, plus 3xh plus h squared, as h approaches 0, if I plug in all the zeros, now what I have is 3x squared plus 3 times x times 0 plus 0 squared. Whoops. Okay, so that 0 is just going to be 0. That's just going to be 0. So the derivative is just going to be this, 3x squared. That is the derivative, or that is f prime of x is equal to 3x squared, right? And that leads me to derivative notation, right? So I kind of skipped over this at the beginning of the lesson. Looking at page 97 helped remind me of it. So this is derivative notation. The main way that we'll do is we'll just write f prime of x. There's a lot of different ways to do derivative notation, though. Let me show you. Let me count them. All right, so the first one, the derivative can be written as f prime of x, and I guess the interesting thing about this is every single notation I'm about to put down for you are just different ways of writing the same thing, meaning to differentiate or to give you the derivative of this function. So f prime of x is one, or another way they do it, they'll just put y of x, or sorry, y prime. Right, that's another way that they'll write the derivative. Then there's the ever famous dy over dx, derivative of y over derivative of x. That comes from delta y over delta x, because if you remember, these are tangent slopes, right? So dy dx, or the derivative of y with respect to x. Next we have df of dx, read as df dx, or the derivative of f with respect to x, derivative of f referring to the function as opposed to y. So what we see here is we see some overlap here. We could have function prime of x, or we could have y prime, because our functions have a bad habit of being solved for the letter y. So each notation ends up getting a double dose there. Or the final one is d over dx, or d dx of f at x. This is great. It's like a weird mashup of all of them, of this one in this form. More or less, it's like this is like the unmultiplied version of this times this. So df dx is like this multiplied or simplified. Instead of saying d dx of f of x, I can just say df dx. All different ways to say it, again, as they're read. This is f prime of x, this is y prime, this is dy dx, this is df dx, this is d dx of f of x. That's how they're properly read. I don't read these properly all the time. You'll often hear me say dy over dx or df over dx. Just know I'm wrong. It's supposed to be dy dx, df dx. I just have old habits and they're hard to break. Okay, let's see here. So now that we've got all this derivative notation and all the 5 many ways to write down the same thing, let's see here. Let's talk. Alternate definition of derivative. And we'll stop here. I'll make 3.12 videos, because I think going into almost 30 minutes on the last video, that might be a killer for some of you. So let's break this into 2 videos. I'll stop at the alternate definition of a derivative of a point. So I'll give you the answer before I show you how we get it. The alternate definition of the derivative, instead of doing f of x minus f of x plus h minus f of x all over h, we could say the derivative of a is equal to the limit as x approaches a of f of x minus f of a all over x minus a. Okay? Wow, I can't believe I wrote half of that off camera. Also, that's not a 9, that's an A. So this is the alternate definition. You can see this on page 96 in your textbook. It says derivative at a point. The way this alternate definition works is we take our original definition, right? If you remember f of x plus h minus f of x, the way that worked, or the way we reasoned that, was we had a curve, right? So we had a curve, we had a point on a curve, right? And we were moving an infinitesimal amount to another point on the curve, right? And we knew that this distance of the move, we knew that that was the length of h, right? So this now became point x, right? This point on the line was x, and this value was now x plus h, right? So if I were to do the slope or calculate the tangent slope of that triangle, this rise or delta x would be equal to h, because that's the length of that distance, right? An infinitesimally small amount. And the delta y would have been f of x plus h minus f of x, because the y values are the functional outputs. So right here, the y value f of x would have been the number at this point. The y value at f of x plus h, that's the number value at that point. So y2 minus y1, this is y2, this is y1, right? And so then we're writing that as a fraction over h. So that's how we got f of x plus h minus f of x. Some of you are probably annoyed because I'm going over this again. Some of you are probably thankful because it takes a couple times before this makes sense. Get over it. Now let's talk about this alternate definition. How in the world do I get f of x minus a over x minus a? That's very simple. I take away the knowledge of the length of this line, right? If I don't know how long that line is, say I don't know that it's h anymore, well, then I have to do things in terms of my values of x. If I don't know that that distance is h, I can't call this x plus h anymore. I have to call it an entirely different letter because I don't know what it is. And that's where a comes in, right? So this point, the initial point, they call x. The secondary point, they call a. We don't know what that point is, right? So now my delta y over delta x changes, right? So more or less, this x value becomes x. This x value becomes a, right? This y value becomes f of x, the functional output at x. This y value becomes f of a. So now my slope, or my rise over run, I'm going to do x1 minus x2, y1 minus y2. My y1 minus y2 is going to become f of x minus f of a, right? Because this is y1, this is y2, this is x1, this is x2. So if I do x1 minus x2, then I have x minus a, right? So now my derivative is going to be f of x minus a over x minus a. So it's just a different way to reason it. And you may be wondering, why would I reason it a different way? Well, it's possible you don't know the value of h. It's possible you have a value for a, right? So it's another way to approach the derivative. So we got to get good at using both of these methods, and this is just a different logical approach. So let's do an example with the f of x minus f of a over x minus a, because not only is it a different logical idea of how to approach the idea of a tangent slope, it's also a different solving goal. So the goal in simplifying derivatives using the alternate method is to cancel out this x minus a term. If I can rewrite the formula to where I can cancel out x minus a, then I've got a pretty solid derivative. I'm not going to do the example on page 96. You guys have already seen that. Let's pull one from the homework. Let's see here. Quick review. No, not in there. 1, 2, 3. Hey, 3. Use the definition f prime. So I'm on page 101, number 3. Use the definition f prime of a. Sorry, f prime a. Yeah, f prime of a equals the limit as x approaches a. Use this definition at x equals. So use this definition for to find the derivative of f of x of 1 over x at the point x equals 3. So what I'm looking for is I'm looking for f prime of x. So the derivative of f of x. So f prime of x. What does that equal? Well, I have to plug this into this definition, rewrite it, plug in the number 3, and that will give me f prime of x. So let's get to it. Let's switch to green. So let's take the f of x. That's now going to become 1 over x minus f of a. That's now 1 over a. The denominator x minus a. Okay, so the goal is I got to get rid of this x minus a. I can do some complex fraction simplification, right? All those skills are starting to make sense now, why we learned them. Let's do 1 over x minus 1 over a, common denominator. So we'll have a, that'll be x and x. So this rewrites as a minus x over a times x, right? And that's all over x minus a. Well, I may be having performance issues. Why is my computer telling me this? It's saying, well, it's not my computer, it's the recording software. My recording software just said I might be having performance issues. That's annoying. Oh, it says I have too many things going on in the background. Okay, hold on, let me pause. Okay, I think I got it. Should be all better now. I shouldn't try to upload YouTube videos while I'm recording videos. Bad move. Okay, where was I? Okay, yeah, right. We're using alternate definition of a derivative to simplify this with the goal of canceling out x minus a. I've rewritten the numerator as a single fraction. Now I'm going to use some complex fractions. I'm going to put that over 1, invert and multiply. So now I've got a minus x over ax multiplied by 1 over x minus a. So that'll turn into... I've got a minus x over ax parentheses x minus a. Okay, so we're so close here. We've almost got the same thing. The signs are different. So who knows what we can do here? We can always factor out a negative. If I factor out -1, this turns into this positive a turns into negative a, this turns into positive x. You just go ahead and erase that and rewrite it because I'm out of space. So if I factor out -1, I can rewrite that as x minus a. Perfect. Right, so now I can cancel that out. So the derivative is -1 over ax. -1 over ax, but I've also got to figure it out at the point x equals 3. So if I plug in the number 3 as x approaches a, let's see here, it's 1 over 3a, 3x. Hold on, let me reread this. Yeah, 1 over 3a. -1 over 3a. Yeah, so f prime of x should equal -1 over... Oh, wait, no, it should be 3x. I think it's 3x. F prime of x is -1 over 3x. Yeah, because it's as... Excuse me, it's as the limit x approaches the number a. So I'm substituting the number a in for... what am I saying here? X? Hold on, let me just check. I don't want to tell you the wrong thing. It's either -1 over 3x or -1 over 3a. Okay, I got myself. It's both. Okay, where's my drawing? All right, remember how on this drawing I said it's always those letter A's. I'm not used to seeing A's in there. This notation was if we didn't know the value or the distance of line H, but we did have a value for A. So what they're saying is as x approaches A, when they say x is equal to 3, they're telling me that's the value of A. So essentially this value is 3. So when I finish solving this, at this point right here, I will replace that a with 3. So it's negative 1 over 3x. I was mostly right, but I need to finish computing it at the point x equals 3. So if the derivative of f prime of x is negative 1 over 3x, the actual derivative at that point is negative 1 over 3 times 3, or negative 1/9. And that is the derivative and also the limit or tangent slope. Whew. Okay. Where are we at? Oh, no, we still hit 20 minutes. Okay, we're going to pause it for now. That's enough for today. We've got the alternate definition. Remember, the goal when you're doing alternate definition is to cancel out this denominator through whatever means you can to rewrite the numerator. Yep. If you guys have any questions, let me know on the Skull website.